Hey guys, welcome to another day of LeetCode problem solving. Today we're going to invert a binary tree, and as you can see, this problem was inspired because Maxwell, who is the CEO of Homebrew, was apparently shocked when Google told him that, hey, 90% of our engineers use the software you wrote, but you can't invert a binary tree on a whiteboard, so F off. Okay, so today we're going to embarrass ourselves with our crappy programming skills and try this problem out. I've never actually worked with trees, not even for class projects, surprisingly, so this is actually my first try, so bear with me. Okay, now, um, first problem, trees, let's go. Okay, but I do know the tree concept, so I know that there's breadth first search and there's depth first search, and I think the way we need to go about this is we can do a depth first search, and once we've reached the depths of a subtree, we can start, you know, swapping the positions, I guess. Let's think about this first, actually. Actually, no, I'm messing up the terms. Not a depth first search. This is not a search algorithm. We need to find an algorithm that can invert the tree. So obviously we'll be looking at traversal algorithms, um, a post-order traversal, or an in-order or a pre-order, right? So if we do a post-order traversal, let's look at what happens. We'll first go all the way to the end, and then we'll have 9 and swap it with 6. But 6 may have a subtree, so how do we keep going from 6? Because we just swapped 9, right? So there's a problem there. And not only that, but also 7 has its children completely swapped. So how do we know which is the swapped version and which is not? So there's a problem there. So post order is not working for us. In order doesn't make sense so far. Why do we swap this left subtree and then the whole node and then the right subtree? I mean, the positions are getting messed up. So I think a pre-order traversal might work. We start from 4, we swap the 2 subtrees, and then we go to the left one. We swap the 2 subtrees, keep going to the left one, and then we hop back. Yeah, pre-order. Yeah, so we're starting from the root. We're swapping both of the child. So we did the work for the root, and then we go to the left one, swap his children, go to the left one, all the way until the end, and then we swap back and we go to the right ones. I guess that should do the trick, and then we can keep going to the right ones after we are done with the left subtree. And the reason why this might work, this should work is that even though we just swapped 7 and 2 with 2 and 7, let's say, on the first iteration, uh, eventually we'll still swap 2 and 7 because it's pre-order, right? So after swapping the children of the root node, we're going to the left and we're coming back and we're going to the right. So it should work. So I think we just need to do the swapping as we do a pre-order traversal on this binary tree. So, and we can think about the time and space complexities and improvements later on. Let's go step by step. So, let's write a different function, actually. Public void swap node roots. Okay. If So we return the root if it has no children. If it has at least one child, then we need to swap. So this means tree node temp is equal to root dot left root dot left is equal to root dot right root dot right temp. So this is the base case actually, because then we're gonna call recursive. Then we're sorry. Then we're gonna make recursive calls. Invert tree root dot left invert tree root dot right. Cool. So what happens here is the root, if it reaches a point where it has no children, then we just return the root. So this is the base case. Then if it does have children, then we swap it. So we swap it first. So yeah, so basically this is the essence of pre-order traversal and then inversion. We start from the root node. If it doesn't have anything, we just return root. If it does, we swap them. After swapping them, we go to the left, which is in this case 2, right? So 2 has 3 and 1. And then once we go to the left, we repeat the entire process. It has children, so 3 and 1 becomes 1 and 3. Right? So if 3 and 1 becomes 1 and 3, and then we go to the left again, but then we return the root, and then we go to the right, we return the root again. So then we go back, all the way back, all the way back to, I think, 4. Yep. Yeah, definitely. And then we go to 7, same process, we swap it, and then if it succeeds, it succeeds. Cool. Okay. This is 4271369. Let's try this. Oh, sorry. My bad. Let's try and submit this. Okay, why? Oh, okay, right. If root is equal to null, return null. Okay. Sorry. Faster than 100%, less than 54.78. Well, not bad. And that was a fast solution. Okay, this was my first tree problem, and I just solved it. I know it's a pretty common one, but still. And let's see if we can significantly improve this. So what is going on here, really? We know that the tree imitates the same as a recursion stack. So it's just not possible to do this with while loops because while loops have a linear processing of iterations, whereas recursion stacks definitely improve in size. So we definitely need to use recursion stacks. There is no way around it to repeat the process and automate it. And we're not really copying the tree, so I can't really figure out a different way to do this, simply because the way trees are structured, we usually use recursion stacks. And let's see if we can use a data structure. So this is a greedy approach, right? We're not really dividing and conquering. Well, we don't need dynamic programming here because we're not really forgetting the repeated functions. You can think of this as a divide and conquer because we're swapping the tree and then moving down, but it's also a greedy approach because we're moving iteratively towards a better solution. In terms of the use of data structures, let's think about if we can store them in an array and then try to swap it. Here's the thing, even if we stored them in an array, I guess you can come up with a mathematical algorithm where you store it in an array and just swap all of them. But for now, this works. So yeah.